Welcome to our project problem. Our problem had three parts. To begin with, we're supposed to use the comparison theorem to show that that improper integral diverged. Part 2 was taking that function 1 over x and rotating it about the x-axis from 1 to infinity, and then figuring out if we could fill that horn that was formed with 3 cubic units of paint, and if not, how much would be needed. Part 3 had to do with the surface area of that horn, whether to first show that you couldn't cover it with any amount of paint, but then to figure out how much it would take to cover it from 1 to 5. And that was our problem. To begin with, we're going to talk about the first part.
So for part 1, we use the comparison theorem. Okay, so we show that this integral here, 1 over x, square root of 1 plus x to the 4th dx, the comparison theorem will show that this diverges, and that is what we are trying to prove. So we have two functions, f of x, which we're going to use as our original integral here. Well, just what's inside of it, the integral, the integrand. And we're going to use, for g of x, we're going to use 1 over x. So if g of x is divergent, then f of x must be divergent, because if a number that is greater than divergent would be divergent, if that makes any sense. So to show what we did, the function here, or this here, the 1 over x, that would be us finding g of x. And so we just solved this integral, which we got to be limit of, as t goes to infinity, of ln of absolute value of t, which will just end up being infinity, minus ln of 1, which is 0, is infinity, so that we know by the comparison theorem that this integral is greater than the last integral, so that means that this must be divergent.
We are going to let f of x equal 1 over x, and then we're going to revolve it around the x-axis from 1 to infinity. And then we're trying to see if we can fill the horn with 3 cubic units of paint or more if needed. To get the volume of the graph, we should use the formula for a revolving object. V is approximately pi r squared delta y. Since we are given f of x on a finite area, we can just use the f of x as the r value, and then the delta y will become dy because it is infinitely small. We can set the integral up with the volume formula, but then we can take the pi out since it is a constant. In a solid of revolution, the r in the formula is the function that generates the solid, which means our formula to generate is this. Integrating this, we get this long thing, which will end up equaling pi. Thus, it will take pi cubic units of paint, which is a little more than 3 cubic units of paint.
For part 3 of the project problem, we're analyzing the surface area of the horn that we just generated, and how much paint it would need, first of all, to cover the whole surface of the horn, but more specifically from 1 to 5. We do that by finding the general integral for the surface area of a solid of revolution, which we do that by analyzing a cone. If we take a cone and flatten it out, it becomes a sector of a circle. The slant height of the cone is the radius of that circle, and the angle of the sector is 2 pi r over L, where r is the radius of the original cone and L is the slant height of the original cone. So the area of a sector of a circle with radius L and angle x is 1/2 L squared x. Since we know what the angle of a circle is, we can substitute what we've just figured out just a second ago in instead of x and get pi r L. So the surface area of a right circular cone is pi r L. But we need just a portion of the cone because we're integrating. To integrate, we do just slices. So we need the surface area of just a slice of a circular cone. So if we say the top radius of that slice is r1 and the bottom radius is r2, then we can find the surface area by subtracting the surface area of the top portion that we're not calculating from the whole thing, like in this picture. So if L1 is the slant height of the unnecessary portion, and L is the part that we want, then the surface area for the bottom half is pi r2 L1 plus L, which is pi RL for the whole thing, minus pi R1 L1, which is what we don't need. And then we can rearrange that, and we get this equation right here, and then we can simplify that using similar triangles right here to get this, and we can substitute that R2 minus R1L into this previous equation to get pi R1L1 plus R2L. But we don't want that R1 and R2, we just want one radius. So, since we have two different radii over a regular cone, we can just take the average radius, which would be 1/2 of R1 plus R2. Since we have R1 plus R2 there, we just need to get rid of the 1/2 and swap it in, and we have the formula for the surface area of the cone is now, for the formula for the surface area of a slice of the cone is now A equals 2 pi RL. And now we need to put that formula in terms of the measurements that we're actually using, since we don't know what R and L is in terms of an integral of or a solid of revolution. So R, the radius, is the function that the shape is being generated from, in this case 1 over x, and L is the distance from the first radius to the second. Since this is a slice of a cone, that's actually the slant height of the slice of the cone. So it's essentially the hypotenuse of a triangle, where one side is delta x and one side is delta y. So L is square root of delta x squared plus delta y squared. We can simplify this by using the mean value theorem to find delta y. The mean value theorem states that if f of x is a function that is both continuous and differentiable between 2 points a and b, there is a number c between a and b such that f of b minus f of a equals the derivative of c times b minus a. So we know that there are 2 points, xi and xi minus 1, and then xi star between them somewhere that satisfies that rule. If you'll notice, xi and xi minus 1 are two x coordinates, and that's essentially delta x. And f of xi minus f of xi minus 1 is delta y, because it's the difference in y. So the left side of the equation that we got by plugging in those things, the left side is now delta y, and the right side is the derivative of xi star times delta x. So we can plug that delta y, or what delta y equals, into the Pythagorean theorem equation that we just got to get root delta x squared plus derivative of x delta x squared. We can rearrange this and pull out the two x squared, or square roots of x delta x squareds to get just x delta x, and change the xi star to just x to make it a general function, and we get L equals root 1 plus derivative of x squared delta x. So that's our L, and we can plug that into our surface area equation along with f of x instead of r to get the surface area of any solid of revolution is 2 pi f of x root 1 plus the derivative of x squared delta x. And there is our general formula for any surface area of any solid of revolution. Now we just need to plug in the function that we have to find the surface area of the cone, of the horn. That gives us that integral, 2 pi times the integral from 1 to infinity of 1 over x root 1 plus 1 over x to the 4th dx. So from 1 to infinity, we already know this. This is what we analyzed in part 1. We already know this diverges. It goes off to infinity, meaning that the surface area of the whole horn is infinite. We could not paint it with any amount of paint. But we can figure it out from 1 to 5 instead of 1 to infinity, which is the second part. So we just change that, the integral, instead of 1 to infinity to 1 to 5. and then we can evaluate it. So first we change the integrand to, or we simplify the integrand, just like that, to root x to the fourth plus 1 over 3, x to the third. And then we use integration by parts. So we set u equal to root x4 plus 1, and dv is 1 over x to the third dx. We get those for v and du, and then we plug that in and get that mess. And then we analyze the integral of that part and do a u sub where u equals x squared and plug that in the bottom there. And that is a common integral, which says that integral 1 over root u squared plus 1 equals ln of root u squared plus 1 plus u. So if we put x squared back in instead of u, we get that. And then we plug that into the equation we got after integration by parts to get all that, evaluated from 1 to 5. Now we use the fundamental theorem of calculus, which says that if you have a small f of x and a big F of x, such that small f of x is the derivative of big F, or big F is the antiderivative of small f, and you're taking the integral of small f from a to b, then that integral equals big F of b minus big F of a, which is what we're going to do here. The equation that we got after integration by parts and a u sub is our big F of x, and our a and our b are 1 and 5. We plug 1 and 5 in and subtract f of 1 from f of 5, big F of 1 from big F of 5, and this comes out to roughly 1.72223. Thus, it would take roughly 1.72223 units squared of paint to cover the surface of the horn from x equals 1 to x equals 5. Thank you for listening, and good night.